a hopping model. And this one is known as a very popularly known as a spring loaded inverted pendulum model. Okay, this also goes by the acronym SLIP for the spring loaded inverted pendulum. Okay, and what this model is basically, it's basically a point mass body, and then there is a spring attached to it. Okay, so the way we describe the motion of the, well, let's call that as a mass m. The way we describe the motion of this point mass is there's an x and y denote the position of the center of mass. In this case, it's a point mass. And then what we can do is we can sort of magically control the angle the leg makes with the vertical, okay, theta. Uh, when you create a robot, you need to worry about how you control it, PD control, so on. But what we do here is really we just set the angle to be whatever we want it to be when the robot or this hopper is in the flight phase. And then, of course, there's a spring constant. Okay, so if you get this set system, design it the right way, have the right spring constant for a given mass, and the right the angle theta, then you can get it to hop continuously. Okay, this angle theta is known as a foot placement angle, or sometimes it's also called a leg placement angle. So imagine, so this is actually also, people have used this as a model of humans running. So when you're running, they assume that your body is this point mass m, and then you have your legs have a certain springiness into it, and that depends on basically the tendons in your legs. And if you stick your leg at the right angle theta, then you can pretty much run on level ground, also on uneven surfaces and so on. Okay, and so with this model, we can actually learn a lot about controls. Okay, so what I'm going to do is, as usual, I'm going to show you what one step looks like, because that's going to be the building block for the simulation. For the passive walker, we started at the instant when both legs are on the ground, or the point where what is known as a foot strike. In this case, the common place to start this simulation is not at the point where the foot hits the ground, but it's at the apex. So the apex is the position such that so if you assume that this is to be x along the horizontal and y along the y-axis, then whenever the velocity in the vertical direction is 0, that position is defined the apex of the hopper. Okay, when it's at the apex, there's a certain horizontal speed. I'll call that x dot, and I'll put an I just to indicate that step I. At this point, when the hopper is above the ground and its leg is sticking out at an angle, let's call that angle theta I. We can see that the position of the center of mass is at a distance of yi from the floor. Okay, so this is at apex. Okay, at some point of time, this hopper will make contact with the ground, like so. Okay, and then the spring obviously will be compressed, and it will actually travel in an arc. So it'll just go in this direction, and then some point it'll take off. So this is stance. So here the velocity is this way, then it takes off that way. And then I'll talk about the model for the spring. But then eventually the hopper is back in the air at the apex. So now the vertical velocity, the next step, which is I plus 1, is 0. That's when we say that it's at the apex. The horizontal speed is x dot I plus 1. And it's ready for the next step. And of course, this is yi. Okay, so it's apex. Okay, so with this, what we can do is now we can try to write how a step would look like. So there is this phase starts at the apex. So then it goes from apex to stance. Okay, so there is dynamics here, right? Described by essentially Newton's laws or Euler-Lagrange equations. Then there is this time when the leg is on the ground. So this is the stance phase. Okay, so before that, there should be a touchdown. So the touchdown is the phase when the foot just makes contact with the ground. That's when you switch the equations from being in the air to being on the ground. So it's stance. Then there is takeoff, okay, which is here. So let's call that takeoff. And somewhere here, it's going to be this touchdown. And then, of course, we have stance to apex. Then you reach the apex. So this whole thing constitutes one step. And our goal is to model this one step, and then we set it up just like we set up the passive walker. We'll just put those phases together, make one step. For a given speed, we will speed and foot placement angle, theta I. We will find a periodic gait by finding fixed points, and then find the Jacobian to analyze the stability. So that's what we're going to do. So let's start with first deriving the equations for each of these phases, and then put that in MATLAB and see what we can do with analyzing fixed points. So I'm going to copy this. Copy. Okay, so let's just write down all these equations. Okay, I think it's easier to first look at only the instance, touchdown, takeoff, and apex. So the apex is when y dot I equals, well, y dot I plus 1 equals 0, right? Same. Say apex at step I and step I plus 1. So that's very easy. Let's look at the touchdown. Okay. When it's going to make touchdown, we will see that. So first of all, the spring has its own length, right? Free length. So we'll assume that it's uncompressed. And the moment it makes a touchdown, so the length is L0, there is an angle theta. Okay, so we can see that it'll do a touchdown when yi equals, so yi is basically the height, L0 cosine theta. So whenever this happens, or yi minus L0 cosine theta equals 0, we'll have a touchdown. So that will be our event. So by the way, this is an event for the ODE. This also is going to be an event. Okay, next, let's do the takeoff. Okay, so when takeoff takes place, okay, what will happen is that the force from the ground onto the hopper is equal to 0. That's when takeoff takes place. So that happens when the force, which by the way, the force in a spring is given by K times L minus L0, right, equals 0, which means that when L equals L0, we'll have takeoff, right? So what L0 is a uncompressed length, which we all know about. We need to just find L. So we know that this is X comma Y. This point, the contact point, is going to be X, C, and 0. What is XC? Well, XC is the position where the touchdown took place. Okay, the touchdown place is not going to change. We can find this XC just by looking at this figure. Here you can see that the touchdown XC is basically given by, if this is XI, then XC equals XI plus L0 sine theta. So we know the XC, the touchdown location, or the X touchdown location, just from looking at the touchdown, analyzing the system at touchdown. Okay, so we have XC. And we know what, we need to find what L is. So we can see that L is basically the distance from this point to this point, and that's going to be the Euclidean distance. So it's going to be from Pythagoras theorem, L square is x minus xc square plus y minus 0 square. Basically the difference between this and this point, and then you square it. So which means that we have L equals x minus xc square plus y square. And so the condition is x minus xc square plus y square minus L0 equals 0. So maybe I can just underline all these things. So this is one, which changed to a different color, blue maybe. This is one condition. Here's the other one. That's for the event for ODE 4.5, and this is the third one. Okay, so these are the conditions which determine when these phases will take place. So we have covered all of them. We've covered apex, touchdown, takeoff, and apex. Now let's look at these phases: apex to stance, stance, and stance to apex. Okay, we'll write the equations for those phases. Now for the fourth one, apex to stance and stance to apex. Okay, what's going on in this phase is that the pendulum or the point mass is moving under gravity. Okay, the spring is not really doing anything here. The spring cannot act on the body because it's in free air. So in this case, the equations are pretty simple. It's basically the acceleration in the x direction is going to be 0 because there's no force in the x direction, and the acceleration in the y direction is minus g. So that's the equation for stance, the flight phase. Okay, both those represent the flight phase. Right. Okay, which is basically a ball dropped under gravity. The final one is going to be the stance phase. Okay, in the stance phase, the mass is in contact with the ground. We said this point is xc, comma 0. This point is x, comma y. There's going to be a force due to the spring. And then we can write equations either using Euler-Lagrange like we've done, or using free body diagram. So let's just use Euler-Lagrange. So the total energy is going to be, the kinetic energy is going to be half mass times velocity square, which is basically x starts, I forgot the mass, m divided by 2 x dot square plus y dot square. Then we have the potential energy. Now we will have mass times gravity times y. That's the potential due to gravity. And then there's going to be a potential due to spring. So that's going to be half k times L minus L0 square. Okay, now we've seen that L is x minus xc square plus y square from the previous page. So all we need to do is write down the potential as mgy plus half x minus xc square plus y square minus L0 square. So that's the potential. The Lagrangian is t minus v. And then to find the equations of motion, we do d dt dl dq dot minus dl dq equals Qj. Here, since there are no external forces, we've accounted for all forces through the potential. Qj is going to be 0. Small qj is going to be two things, x and y, corresponding to the 2 degrees of freedom of the system, the x and y position. Okay. So if you do the math on this and find the equations, you end up with equations for the stance phase which look like this. Equations of motion, they are mx double dot equals k L0 minus L x minus xc divided by L, and then my double dot equals k L0 minus L y divided by L minus mg, and of course L is x minus xc square plus y square. Okay, they look a little bit complicated, but they are not so complicated, right? But they are nonlinear. Clearly, they are nonlinear because of this term. Okay, so those are the equations which will go in MATLAB. Okay, so that's we got all the equations. So if you go back to the phases, we have the apex, we have all the events which we have already written the equations 1 through 3. Then we wrote the equations for apex to stance and stance to apex, which are the flight phase, which is ball falling under gravity, and the stance phase, which are more complicated, which came from Euler-Lagrange. Okay, so once we have these things, we can then set up a simulation which will do one step, okay, which have all these phases. And then once we have this one step, we can then find the fixed point and then do the stability calculation. So here is the This is a simulation of a hopper. I've put some parameters for the mass, spring constant, and so on. So let's look at the ingredients of this. So first of all, parameters. In this case, I've used mass of 1 kg and then spring constant of 100, and I fixed the foot placement angle to be 10 degrees. Okay, and as I said, for 10 degrees, you will get a certain solution which is periodic, and then the goal is to find that solution. This is an initial guess on what that solution might look like. Initial guess. So the thing which I forgot to mention here is, even though there are 4 states, position, xy, velocity, x dot, y dot, the Poincare map will only have 2 variables. One will be the apex height, y0, and the other one will be the horizontal speed. And that's because at apex, y dot equals 0, the vertical velocity in the y direction 0, and then x, which is the location of the hopper at the apex, is inconsequential. Right? After some time, it will be a distance equal to the step length of the which whatever the step length the robot takes, right? And that really doesn't figure out the equations. That's really a translation variable. So there are only 2 states at apex. So only these 2 states at the apex for Poincare. Okay, so that's
what about the angle theta?
That I fixed that angle. So for a fixed angle, you will get a periodic gate. So think of the fixed angle as a control parameter which is fixed. Just like that, you could also fix the spring constant. Now, if you did not have a spring, you could simulate a spring using a motor. Let's say you had a motor instead of a spring. Then you can change the spring constant by changing the stiffness with which you drive the motor. In that case, that is also going to be a free parameter. So I just fixed those. But clearly there's another way to do this, which is you could fix the x0 dot and y0 and then ask MATLAB fsolve to search for k and theta, which will also work.
Okay, makes sense.
Okay, so here is root finding. period one gate. Then there is the Jacobians for the stability and then the eigenvalues. And then I do some simulations. Okay, so in this case, when I run this code, it does the root finding. It finds the fixed points. Okay, this is basically the velocity, and then this is the height. So the x velocity and height. This is the Jacobian of the fixed point. If you do the analysis by taking the derivative, or sorry, the eigenvalues of the Jacobian, you will find that one eigenvalue is 1. Now, it turns out that one eigenvalue is always 1 for the system. Okay, if you remember in the past when we did the passive Walker, there were 4 eigenvalues. One eigenvalue was always 0. But here, one eigenvalue is always 1. That does not mean that the system is unstable. That eigenvalue actually is because the system is conservative. The energy changes are 0 in this model. There is no heel strike sort of thing in spring-loaded inverted pendulum, because there's a spring, and that spring totally compresses the energy and returns the energy back. So energy is not lost. There is no mass on the foot, so there's no real collision. So for a system like this, you will see that one eigenvalue is 1. That, which I said, does not mean it's unstable. You need to look at the other eigenvalue to analyze the stability. So the other eigenvalue in this case is greater than 1, which means that this hopper is unstable, which means that if you start this hopper with a slight perturbation, it will fall down. And I can show you how that happens. But remember that it is unstable. And then if I go through this, I have a set of functions which are essentially the same as that of a passive Walker. Okay, that's the same. These functions are copy pasted from passive Walker. The one step is copy pasted, but I had to modify the phases, right? I need to put the equation. So apex to ground. So this is apex to stance, which is basically an ODE 113. Now this is another solver I used. I found a little bit better results with ODE 113, but you can use ODE 45, which will do the same job. In this case, I have the flight phase equations, and I also detect contact. The equation I wrote down, which was I believe it was y minus L cosine theta, that's in contact. Then I have a phase when we have the stance phase, in which case you go use ODE 113, and then there's an event called release, and that release event is basically the fact that L equals L0, which I wrote down on paper. And then we have the ground to apex, which in this case is again the flight state equations, but we have the apex condition, which is that the vertical velocity in the y direction is 0. Okay, and I forgot to say, had these stance phase equations for the previous one. Okay, and so the equations for that, the flight phase equation is really simple, falling under gravity. Then I have the contact condition, which I wrote down was y minus L cosine theta equals 0. The stance phase equation is a bit more complicated, but it's all in here. Then the release condition, which I said was L minus L0. This is robot.L is the natural length of the pendulum, of the spring-loaded pendulum. So that's L minus L0. And then I have the apex condition, which is basically saying that y dot is 0. And then the animation routine is, you know about. Okay, so that worked. What I can do is I can show you that this is actually unstable. So here I am getting the fixed points, I'm getting the stability, and then I'm simulating the system. So I choose the fixed point to simulate. Now, if I do it this way, keep the fixed point. Don't use a fixed point, right? The fixed point is if you start the system exactly at the fixed point, then it's not going to fall down because there are no disturbances. However, if you start the system slightly away from that fixed point, so let's say that what I do now is I say z star, or let me say z0 is z star, okay, and z star is these two states. I'm going to add a small perturbation, 0,1 times 1, 1. So that's adding a 0.01 perturbation to position velocity. So I don't know if this will fail, but we can just see what happens. So give that, and then let's start this. So it'll again do the whole thing of finding fixed point stability, and then maybe it will not fail. Maybe this is a too small a perturbation, or maybe the steps are not enough for it to fail. Yeah, so you see it failed. It actually penetrated the ground again. This is a sign it failed. So it's unstable. If you do a perturbation which is 0.01, this thing falls down.